All right, today we're going to work on actually, I guess, a beam, a moment of inertia, and a flexural stress all in one big problem. So kind of all the stuff that beams have been dealing with. Quiz 3 does open up today, so you've got a week until the 17th to finish off quiz 3. And I think that's kind of it for you. Well, you have the lab. The lab is available to do now, so you should be able to work on that. The parts, if you didn't get one of the little samples there in the room, the machine was set up the other day, so I think it looked like it was ready to go. I doubt anybody else is going to change the settings, but do make sure that it's, you know, reading in pounds and peak hold is on and all that kind of stuff. Let's set up a problem here to solve. And let's do one that's going to require us to calculate a centroid and also calculate the shear and bending diagram and calculate the flexural stress. So let's do a beam that we haven't done, and we haven't done. You have some in web work, but we haven't done any of these really outside of web work. So this beam is going to be a cantilever beam. I know there's at least one of the web work problems that deals with this one, but cantilever, so it's stuck into a wall, or it's bolted to a wall, or it's welded to a wall, or it doesn't have to be a wall, but it's attached to something at only one spot. So it's got one of those fixed supports. We did do a frame problem that had a fixed support, at least we did part of it. So this one is one of the ones where instead of having a reaction in the vertical and a horizontal at a pin plus somewhere there's a roller, then this one has all of the reactions at this fixed support. We'll put some forces on it. Let's put a distributed load kind of over here. Let's put a point load at the very end. Let's put a moment in here somewhere. Let's say that this is 4 feet. Let's make this one 2 feet and this 2 feet. And let's make our point load 2 kips. And then let's make our concentrated moment. This one's counterclockwise, so it'll be negative when we get to our moment diagram. Let's make it 3 kip feet. And then let's make our distributed load 1 kip per foot, 1,000 pounds per foot. Okay, so we got that. Let's say that this thing is a beam that we have created. We're actually going to turn it into kind of a T-shaped beam, so we would see something like this on the side. And the cross section of this thing is going to be a plate of metal welded on top of a T. So a standard T, we'll go grab out of the chart somewhere, WT something, we'll look up some numbers. And then we wanted it to be a little stiffer, so we welded on another piece of metal on top of the T. So we've got some numbers we can look up, but some addition to that to deal with because we've made it stiffer by making the flange thicker. No. There we go. Well, it still looks a little longer, but it's centered on the thing. Yeah. No, it's actually going to be longer than the T, but centered. Yeah. It would, if we didn't do that, like if we did like this or something, then it would create other issues for us that we're not ready to deal with. So we're going to center it up and make it a little bit wider than the T. So we can put a little fillet weld right in here and right in here down the seam. All right, let's do our shear and bending moment diagram first. Let's do that part first. So what we need for that is we need to figure out what our reactions are going to be here, because we do have to, you know, disconnect it from the wall somehow and figure out what's going on back here. So we still do have, just like a pin, we have, and we'll assume that was point A, so AX, but that's zeroed out because none of these forces are angled, even though I kind of drew some of them crooked, but none of them, they're all vertical. And the moment doesn't create reactions in the X or Y direction. We'll have an AY we need to calculate, and then we'll have a concentrated moment. We'll make that concentrated moment, we'll draw it this way. Moment at A. All right. So probably the simplest thing to do first is the summation of forces in the Y direction. We've already decided that AX is 0, so we don't have to worry with that one. Our 1,000 pound per foot distributed load, we'll lump that into a 4,000 pound load or 4 kip load, and we'll offset it 2 feet over there, 2 feet. So that would create a, oh, I'm not doing moments, I'm just doing a summation of forces. So it's a 4,000 pound negative because it's pointing down. AY is pointing up, so let's put plus AY. Minus 2,000 pound point load at the end, that's minus. Those add to 0. So I've got 6,000 going down, AY has to push up with 6,000. Or 6 kips if you want to do kips, which we'll probably, when we draw our diagram with shear and bending diagrams, we'll probably put those in kips just so we don't have so many numbers floating around out there. So this will be 6 kips. Okay, now we can do our moments about A, assuming that's point A over there on the left end of the beam. Let's say clockwise is positive for this equation. I drew the moment at A counterclockwise, so we'll get a negative moment at A. And then I've got a plus 4 kips. It has a moment arm of 2 feet. We've got a counterclockwise moment, which is going to be negative in my equation here. So minus 3 kip feet concentrated moment. And then I've got a clockwise, which in this equation will be plus, so plus 2 kips with a moment arm of 8 feet. Those need to add to 0. So that'll give me, if I move the moment at A to the other side, it'll give me moment at A equals, and then we got to do some math. So 4 times 2 minus 3 plus 2 times 8. 21, and that's going to be kip feet. And it is 21 kip feet. That number came out positive, but I drew the arrow for it counterclockwise, so it's negative 21 kip feet in my moment diagram. Okay. Let's see, what else do we have? I guess that's all. We already decided that AX is 0. So now we can go down here and work on our shear and bending diagram. So this one, let's put our shear, let's just put it right here. V equals 0, our units will be kips, so that we don't have thousands of numbers to put, we just have tens or less. So it's going to go up AY, so it's going to go up 6 kips, and then it's going to go down 4 kips, and then it's going to go down 2 kips. So we're going to stay positive the whole time, and we're going to max out at 6,000. So let's just make these 2, 4, 6 kips. So like I said, it starts at 0, but then almost immediately the reaction at A happens, which is a plus 6,000, so it goes up to 6 kips. Then the distributed load also takes effect at that same point, and it's a negative 1 kip per foot. So I was at 6,000, I drop 1 kip per foot for 4 feet, so I go down to 2,000. And it's a constant or evenly distributed load, so this is a constant slope, negative slope of 1,000 pounds per foot. Then there's no change in shear. There is a concentrated moment, but that doesn't change the shear. So it goes straight across until it gets to the minus 2,000 pounds, which gets me down here. So that's 2 kips. This was 6. Okay, now I need to calculate the areas of these. So I'm going to divide them up where this little piece, this piece, and these 2 pieces. So this one over here has a height of 2 kips and a base of 2 feet. So it's going to be 4 kip feet. So with this one, 2 times 2 is 4. This one I have to be careful with. So the rectangle on the bottom has a height of 2, a base of 4, so it's 8. The triangle has not a height of 6, it only has a height of 4. You know, this distance is only 4. Wow. How do I get rid of that? All right, this distance is only 4. So a height of 4, base of 4, but it's a triangle, so 16. And then I can begin to create my bending moment diagram. Now the bending moment, well, I guess I could shade the thing in, then not totally necessary. Oh yeah, it's 8. 8. 4 times 4 divided by 2. So the total of these is 16. All right, the bending moment diagram here, if you think about the beam, let's go down here real quick and think about if we have a cantilever beam and it has, you know, a distributed load, a point load. It does have this counterclockwise moment over here, but in general, this thing is going to bend in a way that more or less, you know, does something like that. That puts tension on the top of the beam and compression on the bottom of the beam. Bending moments that put tension on the top are negative. So this is going to be a negative M. So when I'm drawing my diagram, if I do what I normally do and I start down here, it's all going to happen down in this region because it's all going to be negative. So it's useful at least to take a second or two and figure out where do you draw your reference line. I want to draw it way up here. So my M equals 0 kip feet. It's actually going to be higher than I would normally put it just because most of the bending or all of the bending moment here is going to be negative. And I have this starts out at negative 21 kip feet. So it'll start out negative and then it'll gradually get higher and higher, but still remain negative. So that's why I'm putting it down here. So I do need to get down to negative 21. So let's put 5, 10, 15, 20. Do that, and then negative 5, negative 10. Maybe that'll work. And then, like I said, the very first thing that happens, we start at 0, and then you do have to be careful. When I calculated this number, I calculated a positive number, but that positive there means I drew this arrow in the correct orientation, and I drew it counterclockwise. And in my shear and bending diagrams, we have agreed that for all of this course, we are going to create bending moment diagrams that represent counterclockwise moments as negative numbers. So this is correctly drawn as counterclockwise, so I have to put a negative 21, which will get me down to, whoops, I want to draw with that, down to here, negative 21. And it's going to be a step change from 0 to negative 21. Then I will begin adding these shear force. When I integrated my shear diagram, those are all positive. They're all above the 0 axis for shear. So I'm going to add and hopefully get to 21, although it doesn't look like I'm going to get, oh, well, I've got the concentrated moment in there. well, see what's going on. All right, well, let's carry on. This is a 16. I'm at negative 21 plus 16 gets me to negative 5 right in here. Now this one's a weird one. It has a section, you know, the rectangle underneath that is constant, but it does have a slope on the top of this. So this is a curved line in my bending moment diagram because the shear is changing, but there's a part of it that's also constant. So it just means the slope doesn't change as much as if it doesn't get all the way to horizontal, right? A lot of times these things go to 0 and it gets to be a horizontal line. So all it means is at the end, I don't end up horizontal. So I will go a high number in shear, so I have a steep slope, so, you know, kind of going upwards, and I end with a lower number, which is horizontal, but not 0, so it's not close, it's just kind of close to horizontal, and then I can fill in, it must look something like that. And then I have a straight, I add in 4, right? So I'm at negative 5 plus 4 gets me to negative 1, which is probably right in here. Now, if I look at these closer, then I really should have continuity. So this slope probably does more like that. Let's see if we can straighten them out a little bit. Yeah, this is negative 1. This is negative 5. So negative 5, I added 4, so I'm at negative 1. And then, don't forget, I've got the counterclockwise 3 kips. So I'm going to subtract off. Counterclockwise moments are negative in my moment diagram. So I'm at negative 1. I want to subtract 3. Gets me down to negative 4. So maybe right in there somewhere. And then I have a positive 4 in the last section of the shear diagram. So that gets me to 0. So it's got this little sawtooth looking piece in there. And turns out our maximum bending moment for the cantilever beam is right there at the wall. And that's just going to be true. There's not a way to prevent that really because of the way the cantilever is supported. You push on this beam, cantilever beam out here, and if it doesn't have any other supports, then the maximum moment is going to be at the wall. If it has another support, like if there's a roller somewhere under it, now it's statically indeterminate and I can't deal with it yet anyway. So when you have, there's a couple of these special cases. So cantilever beams, if all you're looking for is the maximum bending moment, then it's at the wall. Simply supported beams, we'll take another little aside over here. Simply supported beams, doesn't matter how, pin and roller, roller and pin, whatever. If the loading and supporting is symmetric, so this would be symmetric, right? I've got a point load in the center and the loads at either end, then M max is at the center of this beam. And you don't have to go draw, if all you want is the maximum bending moment, then you don't have to go draw the whole shear and bending diagram. You can just know that, hey, as long as the loads are symmetric and the supporting mechanism is symmetric, then the maximum bending moment's at the center. And it doesn't have to be like a point load. It could be a distributed load or some combination of loads. We could have, something like this. That's symmetric. We could add a point load, still symmetric, as long as we add symmetric point loads about a center line. As long as there's symmetry about that center line, then the maximum bending moment, even for a simply supported beam, is going to be in the center of it, center of the span of the beam. So there's some instances where you might have a problem with a whole bunch of stuff on it, but if you're only trying to figure out maximum flexural stress, and you need to know the maximum bending moment, you don't necessarily have to go draw the whole setup here if it's one of these scenarios where you know where the maximum bending moment is. You can just calculate it directly. So we could have stopped when we were right here had we known that the maximum bending moment for a cantilever beam is at the support, the fixed support, the wall in this case. we would have to recognize if it is it a positive or negative moment so that we know, you know, where's tension and where's compression. But so for us, this is a negative 21 kip feet maximum bending moment. So M max. As far as our equations are concerned. Now we got to deal with this cross section because we're trying to find flexural stress. So we want to know the flexural stress in this beam, maximum flexural stress probably, and we have reinforced the beam. So let's go get some more dimensions on our beam cross section. Let's take the T-beam and then let's put our plate on top of it. And we'll have to get our reference material. Let's see, in here and in here. And then we're going to look at the WT part first. Let's open that. All right, let's get, well, last time we did the WT 6x60. That's okay. Let's make it green. Let's make it a little larger this time. Let's do WT 8x50. So this row. All right. So we're going to need the moment of inertia for this part, 76.8 inches to the fourth. We're going to need to know where the centroid of this T part is so that we can figure out where the centroid of the combination of these is located. In doing that combination of centroids, remember you have to do the area times the centroid. So we also need the area of this beam. So we need that. We probably need the exact depth of the T also. We know it's close to 8 because it's WT 8, but we need the exact depth of it. The other things are not going to be necessary for us specifically. It does look like it has a 10-inch flange, so we'll make our metal piece that we put on top of it like 11 inches so it hangs over a little bit, quarter inch on each side more or less. And I think we'll be good from that point. So let's get these numbers transferred over. Oh, and so W8x50, WT 8x50. So this guy is WT 8x50, and it had an area of 14.7 inches squared. It had a depth of 8.485 inches. It had a moment of inertia about the x-axis, which is the one we need, of 76.8 inches to the fourth, and then it had y sub c measured from the top of the beam of 1.76 inches. Okay, and let's say that our plate that we've put on top is just a flat plate, and it is, we want to make it 11 inches wide, and let's make it a ½ inch thick. And then however long the beam is, 8 feet long. Okay, so let's mark in the very first thing before we combine these things into one common beam, reinforced T-beam, then we need to know where the neutral axis of our combined shape is. So we know where the neutral axis of the plate is. It's, you know, right in the center, a quarter inch into the beam there. So that will be X1 if we call that flat plate part 1. We know also from our chart where the neutral axis for the T is. It is at a distance of 1.76 inches from the top. So right here, 1.76 inches. We just need to know where these things are, you know, what is the combined. So this distance is the depth, which we know is 8.485. And let's make this part 1 and the T-beam part 2 and put our little chart together. So part 1, part 2, the area of these. Area of part 1 is 11 by a half inch, so 5.5. Area of part 2 is from the chart, 14.7, so 20.2 inches squared. Should check to make sure I'm not making mistakes here. All right, good. And then the Y for each part, I'm measuring everything from the bottom. You know, this is my x-axis down here. I'm putting y-axis right through the center. So for the part 1, I go up 8.485, and then I add half of the thickness of the plate, which is a half inch, so I add a 1/4 inch. So I go up to 8.735 inches. And then for the distance from the x-axis to the x2 axis is the depth of the beam, 8.485 minus the centroid, 1.76, so 6.725. And then I multiply these two together to get the area times location of the y centroid. So 5.5 times 8.735 is 48.0425. We'll just carry out all that. 14.7 times 6.725, 98.8575. We add those two numbers together, and we get 146.9 inches cubed, and we'll have y sub c is 146.9 inches cubed divided by 20.2 inches squared, 7.27 inches. And then we look and see if that makes sense. So it was at, just the T by itself, it was 6.725 inches above the very bottom of the T, and now we've raised that up to 7.25, which makes sense. You know, if we weld this plate on top, then that's going to shift the centroid up some amount, and it seems reasonable anyway. So 7.27 seems like a reasonable location for the centroid of the T-beam with a plate welded on top of it. Once we know that, then we can go in and calculate our moment of inertia for the combined T with welded on plate. So I for part 1 about the neutral axis. So neutral axis for part 1, too many subscripts there, is I1, part 1 by itself is just a rectangle, plus the area of part 1 times the distance between what I labeled as x1 and the neutral axis, squared. So we plug in, so we'd have to know what is the moment of inertia of a rectangle. So you'd either go look up the equation for that. That's one of the things that you'll have on the reference sheets for the exam, is you'll have that chart from page 419 that shows all of the moments of inertia. If you don't remember, then you can go check that. For a rectangle about its own centroid, I is the base times the height cubed over 12. Or you can look it up. And remember, there's also that x prime axis that you only want to use the Ix prime from the charts when the that is the place that you want to calculate the moment of inertia. You can't apply the parallel axis there. Remember this thing that I've got written out, this equation I1 plus A1 x squared, y squared, whatever, is the parallel axis theorem. You cannot apply the parallel axis theorem to the x prime equations because it's already been done to them. That's how they became the x prime equations in the first place, is that someone took the Ix, bh cubed over 12, and applied the parallel axis theorem. So like if we did that, let's just take that real quick. So x prime is down there, right? So Ix prime would equal Ix plus area of this part times y squared. So Ix is BH cubed over 12. The area is BH, this is plus. The distance between them is H over 2, but it's squared. And then I have BH cubed over 12 plus BH cubed over 4, right? And then when I combine these together, that becomes BH cubed over 3, which is, that is the equation for that you would find in the chart. So it's already been done to figure out the x prime. You can't take that and do it again. You'd have to go back to the original x. So you can use the x prime equations, but only if you don't apply this part. You don't use the parallel axis theorem. You have to use them as they are. Okay, back to what we were actually doing. The moment of inertia for this plate is the base of it. We made 11 inches. We made the height of it 1/2 an inch. And you divide by 12. It has an area of 11 times 1/2 an inch. And the distance between its neutral axis, what x1 is, and the neutral axis for the whole part. So we have to calculate that. x1 was our y, the y centroid of part 1, which I labeled the x1 axis. It was at 8.735 inches from the bottom. The neutral axis was at 7.27, so I'm subtracting these two numbers. The difference in them is 1.465. I left off my units on a lot of those numbers, so that's why they're not showing up. 0.5 cubed times 11 divided by 12. So by itself, the little flat plate, actually it's not little, it's 11 inch wide, 1/2 inch thick sheet of steel. But its moment of inertia is pretty small, 0.1146 inches to the 4th. But we did raise it up above where the center of the bending for this beam is going to be, the neutral axis. So it increases the moment of inertia to, let's see, 1.465 squared times 0.5 times 11, 11.8. So the combination of those two numbers, 11.9 whatever, is the moment of inertia of the plate. Now we need to add in the moment of inertia of the T. So the moment of inertia about the neutral axis for part 2, the T, is its moment of inertia, which is, we just looked up out of the chart, plus the area of part 2 times the distance between its centroid axis and the neutral axis of the whole part, squared. So we looked up the moment of inertia, and it was pretty big, 76.8. And then it had an area, we also looked that up, 14.7. And the distance between its centroid was located at 6.725, and the neutral axis is located at 7.27. So the distance between them is 0.545, negative 0.5, but it gets squared, so that's okay. So we 0.545 squared times 14.7. This term is 4.37 and then 76.8. So if we add this, and this, that will be the total moment of inertia of the whole thing. So let's see what that is. 4.37 plus 76.8 plus 11.804 plus 0.1146. So if we did all those numbers right, which we probably should go check, we would have 93.1 inches to the 4th for the moment of inertia of the T with the plate welded on top of it. Now, we're making some assumptions. We're making the assumption that these things do behave as one object. There's not a difference between them. That may not entirely be true because, if you really did build this, then you probably welded here and here, and between them, there may not be anything. Maybe you put some kind of adhesive between them or something, I don't know, but they might not behave exactly like something that was made all as one piece. But assuming that they did behave all as one piece, this would be this moment of inertia, assuming we did our calculations right. But it's probably a little bit less than that because there's a good chance that the plate is not behaving as, one with the T. The little interface between them right here may not be acting exactly like two parts made as one. So you do have to take into account there's different things that can happen there that could make that better. Like you could put some kind of adhesive between them. You could do a friction type weld. Now in this case you really couldn't friction weld an 8-foot long plate on top of a T-beam, but there's ways to make those behave more like one individual piece versus what we did where we just welded along the edge of the thing. So having that number and M max, we should be able to calculate sigma, flexural stress in the beam. We have enough info to do that now. So we know that our maximum bending moment was a negative 21,000 foot-pounds. We know that Y, if we go back to this picture, probably should be, we never drew our neutral axis on here. It ended up somewhere in here. And it was at 7.27 inches from the bottom. So it looks like the largest value that we can put for Y would be to measure from the neutral axis down to the bottom of the beam, the 7.27 inches down. So it'd actually be negative 7.27 in our equation. If we wanted to know the stress on the top of the beam, then we'd use the other direction, but it's going to be a smaller value for Y. And we put a smaller value in the numerator of this equation, it generates a smaller stress. So we'll assume that we want to know the largest magnitude of stress. So we put in a negative 7.27 inches for that. We have unit problems here. We have feet and inches. So we'll convert our feet 12 inches per foot so that we're in inch pounds in our numerator. Well, inch pounds times inches. And then our moment of inertia, the one we calculated, said 93.1 inches to the fourth. So those units will work out to give us pounds per square inch. And we have negative, 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 so it ends up a negative number. So it's a compressive stress. 21,000 times 7.27 times 12 divided by 93.1. So 19,678.2 psi, or negative 19.7 ksi. So now we're kind of getting close to where we don't have a huge factor of safety against yielding. If this is steel, then the compressive strength of steel, or the yielding strength of steel and compression, is in the 30,000 range. So we're at 20,000. So we've got a little factor of safety against yielding, but it's not huge. And we made the assumption that when we welded these plates together, the flange and that plate together, that they are behaving as one piece, which they probably aren't exactly, which would reduce our moment of inertia a little bit. It's not 93.1, it's probably a little lower than that. And if that number gets down to some value, then our stress will be at 30,000 and we might be yielding our beam. So in this class, we're not so concerned with the failure modes and everything. We're more concerned with calculating a factor of safety, so which we could do. We calculate a factor of safety, or given a factor of safety, calculate something. This would be an interesting problem if you were given that you need to maintain a certain factor of safety against yielding, and then how thick do you make that plate? There'd be a lot of variables in there, right? Because the thickness of the plate changes the location of the centroid. The location of the centroid changes every one of these moments of inertia. So there would be a lot of dependencies if you had that kind of problem. It'd be interesting, but it's not like a test problem. Yeah. A test problem, this one, if you were given M max, then this is a test problem to calculate flexural stress. This is a decent test problem just to calculate the moment of inertia, though. It's a harder one to calculate the moment of inertia because you have to calculate the centroid of the combined shape, and then you have to calculate the moment of inertia of the two and combine them together. So I would think getting to that 93.1 number, that would be kind of a upper level test problem. Getting to that 19 KSI, the 20 KSI number, that one's probably more than a single test problem. It would have to be multiple test problems. Yeah, it took us 40 minutes to do it. Now we were talking through it, but still, it would take more than 6 minutes to do, I think. If you had to, well, so there are efficiencies. We didn't have to draw the shear and bending diagram, right? We could have just written the moment equation and gotten our 21. And then this part's still kind of cumbersome. It's not a faster way to go about finding the centroid of these two shapes and then finding their moment of inertia. Obviously, you wouldn't have to do the little X prime thing on the side there, but it would still be probably more than I would ask on a 6 or 7 minute test problem. I have asked this before though, just given that, calculate the moment of inertia. I have asked that before. There's another type of this where maybe it's an I-beam and you weld the same plate on top and bottom, so then you don't have to do the centroid, right? It's just in the center still, so it speeds it up.
Are you going to ask us to draw the graphs on this one?
No, on the exams, the graphs are either part of the problem, so I give you the graph and then you go, read numbers from it to solve something, or it looks like this. You're given beam, and it's got some loads on it, and then you're given a set of shear diagrams, and one of them might be, I don't know, something like that. One of them might be this, and you're given 4 or 5 different potential shear diagrams to see what one matches it. You're not given numbers. These are like letters, P, W, and only one of them would work. All the others are, something's backwards. You have well, this one, pretty clear that it can't represent that combination of distributed load and point load because there's no step change underneath P. This one, it's showing a negative value for A1, so it can't be that one. This one shows a positive reaction at A, then no change, then a negative P value, then no change, then a slope downward, and then an upwards at point. So that one could be the shear diagram for that picture. And so it's stuff like that where it's all, you figure out, well, this one can't represent it because of this reason, and this one can't do it because of that reason. This one works in all the scenarios. It must be the one. So, and I'll either ask, I'll give you the thing and ask you for the shear diagram or for the bending moment diagram to select between 4 or 5 options that I've drawn out, and only one of them would actually work. So that's how we test for shear and bending diagrams. Any other, you're either given the diagram like this, and you're asked to solve for a flexural stress or something like that. There's only, well, we haven't looked at it yet, have we? Let's see if it's posted in here. There should be in exam 2 a list of the questions. Let's see. Oh, it's always so slow. Well, in exam, there we go. In exam 2, there should be, like there was in exam 1, where there's a outline. Maybe this one. I may have to go track it down, but let's see if this. Oh no, that's actual. Hey, there's some worked out frames and machines problems. Well, I'll have to find a list of the outline for the exam, but there's only a handful of questions that have to do with shear and bending diagrams. Most of them are more focused on flexural stress and moment of inertia and things like that. And then there's at most 2 that are dealing with shear and bending diagrams, just because they're hard to ask a test question about. All right, so I think that is all we need to do. We're going to come back on Monday and do one more beam. Actually, there's still a whole week worth of beam topics, but you've got your quiz 3 is open. You've got the lab. You can go run your test sample. It should be open, and the machine was set up last time I checked it, which was yesterday. And I think we're good on all of that.